Okay, now we'll solve some problems on cylindrical coordinates, and I'll also talk about spherical coordinates. On Thursday, we'll look at general change of coordinates, solve lots of problems, and we'll have our traditional quiz at the end. Okay, so let me solve a few more questions, problems on cylindrical coordinates, then I'll talk about spherical coordinates. Okay, so this problem says evaluate the function, evaluate y over the region E, which is the solid bounded from below by z equals 0, on the sides by the cylinder x squared plus y squared equals 2y, and on the top by the paraboloid z equals x squared plus y squared. Okay, so in such problems, it's always helpful to sketch the region rather than to imagine the endpoints in your mind. Okay, we have a cylinder. This is a circle. Okay, so first draw the cylinder and then we'll place it in the coordinate system. Okay, so this is, you see, this one is x squared plus y minus 1 squared equals 1. So the center is here on the y-axis. This is 1. So this part, so when x is equal to 0, y must be 2, so that both sides will be 1. So this is 2. This is x-axis. And it turns out that this is z-axis. So the bottom of the region is here. On the sides, we have this. And on the top, we have the paraboloid, z equals x squared plus y squared. So again, what do we see in the yz plane? You put x equals 0, you have z equals y squared, so you have something like this. Okay, so this is what you see over there. So let me leave it like this because it's not easy to draw this. It starts from here. So let me pretend that I know how it looks like. So suppose it's something like this, and it goes like this. Okay, so when I draw it, you should expect that there's a bump down here. Okay, so this is the region where we are integrating the function. Our function is this. This is f of x, y, z. Okay, so the integral we want is triple integral on E. The region is given as E of y dv. Okay, so now you have to write this in any coordinate system you like. Of course, a convenient coordinate system is preferable. Here, since we have cylinder here, the bottom of the cylinder is a circle passing to cylindrical coordinates, that is polar coordinates in the xy plane, is very convenient. Okay, so we are integrating y. I'll integrate this with respect to z first, and then I have dr d theta. Z enters an arrow parallel to z-axis enters the region when z is equal to 0. Leaves the region when z is equal to this parabola. So this is x squared plus y squared. It is r squared in polar coordinates. Okay, next we have to describe this circle in polar coordinates. But we know what this is. Okay, so this is x squared plus y squared equals 2y. So this is r squared equals 2r sine theta, or r equals 2 sine theta. The cancelled r will be 0 at the origin. The origin here is covered by this. So this is the equation. Okay, so a typical ray R is already inside the region, and it leaves the region when R is equal to 2 sine theta. And this description is valid when theta is between 0 and pi over 2. Okay, so this is theta, no, pi. This is 0, this is pi over 2, and here it is pi. Okay, so between 0 and pi. Okay, so last hour I had something like this, right? Okay. So here, the last thing, I checked the usual things. The last integral is has numerical endpoints, so it will give me a number. Inside I have theta here, so the last thing I integrate is theta. Here I have r. Okay, so there's no there's no constants here, as far as the previous examples are considered. Here you see I had this integral from 0 to 2 pi, and there was no theta here. But here, there is theta here, so I'll do it step by step. Okay, 0 to pi is here, and I have 0 to 2 sine theta here. I'm integrating y. Okay, so y will be replaced by r sine theta. Okay, so I have another r here. I have r squared sine theta. I'm integrating this with respect to z, so z is constant, so it will give me r squared minus 0. Okay, so I have, okay, let me write z from r squared dr d theta. Okay, so, okay, let me do it over here because I will say a few things. Okay, so this is going to be integral from 0 to pi, from 0 to 2 sine theta, r to the 4 sine theta, dr, d theta. Okay, so let's see if I got this. Okay, so sine theta is constant with respect to this, so I have 0 to pi. Sine theta comes out. I have 1 over 5 r to the 5. R to the 5 from 0 to 2 sine theta. I'll integrate this with respect to theta. So this is 2 to the 5 is what? 32. 2, 4, 8, 16, 32. 32 over 5. So that's what comes out of here, 0 to pi. And I have sine to the power 5, another one here, sine 6 theta d theta. Okay, so finally, this is what we have. Okay, now you can easily give it to a software and you get the result. If you are masochistic, you can do this by hand. Okay, so it can be done by hand. If you are a little bit masochistic, you look it up in a table of integrals. Okay, it says sine to the power 2n theta d theta. There's a reduction formula. It reduces this to the integral of sine 2n minus 2. And then, okay, so this in order to integrate this, you have to know the integral of sine 4, then sine 2. Sine 2 is easy. Okay, so it's half angle. You can do it like this. If you are truly masochistic, you can do this because sine square is 1 minus cosine square. You take its fourth power, and inside you'll have again a fourth power of something. So that you can also write 1 minus sine square or 1 minus cosine square raised to a power. Okay, so you can all reduce these. Eventually, you have only sine squares and cosine squares, which you can rewrite as half-angle formulas. So by hand, you can do this. Okay, but of course, you can always, once you come to this step, you can always give this to a software, and the answer will be 2 pi. Okay, and if the answer is 2 pi, nobody suspects it. Okay, so in calculus, this is the kind of answer you expect. Okay, so these are, I have one nice problem in cylindrical coordinates. I want to do that now, and then I'll talk about a little bit of spherical coordinates. By z equals 1, and from the sides, by x squared plus y squared equals 2y, as in the previous one. Okay, let's draw this. You see, this is a cylindrical surface, so we will be looking at cylindrical coordinates. But the trick here is that when you cut this region by z equals 1, and you take the shadow down, the shadow has two different circles. Okay, so that's what we will pay attention. So let's try to draw this. I'll draw this again in the first octant only. Okay, so this is x, y, z. So the first one is this sphere, like this. And I have this. You see this huge sphere, which we are not interested in a lot. And here we have z equals 1. Okay, so the radius of this is 2. So halfway, we have this. Okay. And here we have, so maybe I should use different colors. So this is the bottom of the region we are interested in. Okay. And we have here then I'll draw this. This one is a circle here. It is this circle. Okay, and then we have this. Well, this part I will not, because I'll use this part. Okay, so it goes like this. Okay, so you see this intersects here like this. Okay, so that's the only tricky part in this part. Now, I take the shadow of this green thing. It will be, so this thing drops here, and I have where, well, I'm trying to get this over here, so it's a circle like this. Okay, so the region we are interested in is up here. Okay, so I don't know how to make it more precise, but it's something like this. Okay, so you have this part here. This is the intersection. On this part, you see this part is the cylinder. This part is the sphere. Okay, and we are above z equals 1. So this is z equals 1. Okay, now it's time to write all the critical intersection points. I hope I did that. Okay, so this is 2. So this surface is, the sphere will come to that. So this point, you check this point is square root 3 over 2 and 3 over 2. Okay. When z is equal to 1, okay, x squared plus y squared plus 1 equals 3 equals 4 is this circle. Okay, its shadow is here. Okay, so here we have a cylinder, something like this. Okay, so this is a cylindrical surface. So that using that, I find this intersection point, because that gives me a circle in the xy plane. I have another circle in the xy plane. I intersect them, I get this one. Okay, so this circle, this green circle, is x squared plus y squared plus 1 equals 4 is 3. Okay, so this is, you see, r is equal to square root 3 here. What about the other one? Okay, so that's already given here. This is x squared plus y squared equals 2y. And we did this before. This is r equals 2 sine theta. Okay? So I think these are all the things that we need. This is the shadow of the region here. Okay? And on top of that, you have this slice. Okay? So this part is curved like this. But if you take any point here, an arrow parallel to z-axis enters the region when z is equal to 1, moves parallel to the surface, so it doesn't cut this surface, but it cuts the surface along the sphere and leaves it here. Okay? So now we can set up the integral. And after we integrate with respect to z, now we have to describe this region. But this region, you see, is the sum of two integrals in polar coordinates, because a ray parallel, or rather a ray through the origin, enters the region when the ray is 0, leaves the region along this red circle when r is equal to this, and it does it up to this point. Okay, so let's also find that. What is this angle? The tangent of this angle is this number divided by this number, which is 1 over square root 3, so that is 30 degrees, right? So this is pi over 6. This angle is pi over 6. So when theta is between 0 and pi over 6, the description of r is from 0 to 2 sine, this red one, 2 sine theta. From pi over 6 to pi over 2, it leaves along the green circle, which is r equals square root 3. And this is symmetric on the other side, so I can multiply everything by 2. So that's the volume. So volume is equal to, I'll multiply by 2. So I have two integrals. The first one, okay, so first I wrote here everything in terms of Cartesian coordinates. So since I'm writing in terms of Cartesian coordinates, I should give myself more space. Volume equals, first I integrate with respect to z. Z enters the region when z is equal to 1, leaves the region along this one, 4 minus x squared minus y squared. Then, okay, let's integrate. So since I'm integrating with respect to x and y, I have to find this point. What are the coordinates of this? 3 over 2. Okay. So here, if I'll do xy integration, it is better to integrate with respect to x first, so that I cut it here, and I don't. If I integrate with respect to y here, I have to find the point where the tangent is perpendicular to x-axis. Okay, so that's too much work. So let's integrate with respect to x first. When you are integrating with respect to x first, you enter the region when x is equal to 0, leave the region when x is on this red circle. Red circle is this one, so this is square root 2y minus y squared. And this description is valid when y is between 0 and this number, okay? Because if you pass this, then an array parallel to x-axis will leave the region at a different circle. So this is between 0 and 3 over 2. Plus, I'll multiply this by 2 in a minute. Okay, so again, dz from 1 to 4 minus x squared minus y squared. Then dx, okay, so this time an array like this enters the region when that is 0, leaves the region around this green thing. Green thing is square root 3 minus y squared. And dy, this is valid between y from 3 over 2 up to this point. Okay, so this point is when x is 0, so y is square root 3. Okay, so this is what's happening on the first octant, but I have exactly the same thing on the other octant. So I multiply all of these by 2. Okay, so this is the integral in Cartesian coordinates. Once you set it up, okay, so the rest is easier. Okay, now we can change. Let us change this to cylindrical coordinates. Okay, so let's do this over here. Coordinates. The only thing that will change is the descriptions here. Okay, so let us integrate this with respect to z first. We have 4 minus r squared. So again, I'm multiplying this by 2. 4 minus r squared square root minus 1 here. Then this part will be replaced by r dr d theta. Okay, so here r dr d theta. Okay, r, now we are here. R goes from 0 to 2 sine theta. From 0 to 2 sine theta. And theta changes from 0 to pi over 6. Pi over 6. This is the first part. Plus, now from pi over 6 to pi over 2, I'm again multiplying this. This time, a ray leaves the region along this green circle. Green circle is r equals square root 3. So from 0 to square root 3. And I have exactly the same thing again. Square root 4 minus r squared minus 1 r dr d theta. Okay. So if you are going to do this by hand, this one looks better. And just to check your calculations, I'll write the answer here. So here you compute. And then you get 25 pi over 18 minus 3 square root 3 over 2. Now this is approximately, after all this, you get 1.76 something. Okay? So you see the main idea nowadays in these integration problems outside the exams is to set up the integral correctly. Okay? So the rest will be done by software. If software, sometimes the software takes it, thinks about this for a minute or two, and then write exactly the same thing back to you, meaning that somehow it couldn't, its algorithm didn't work on this one. Then you change to other coordinates, try again. So it should be able to do one of those things. If nothing works, of course, if you are interested, normally we are interested in this number. Then you just say, evaluate the integral numerically, and then you'll get some number. Okay. So again, the important thing is to set up these things correctly. Okay, there is a nice problem again with the spherical coordinates, cylindrical coordinates. Okay, maybe I can solve this on. And I have another thing here. So, okay, I'll solve these on. But these are very interesting problems, so let me work on them here. Okay, so here's a typical problem from last year's. Okay, so let me write the problem here, then I'll erase this and solve it over there. Or maybe, okay, so let me solve it here. Okay, so we have a container of the form. So what is this? Z equals x squared plus y squared. And z is positive less than or equal to 10. Okay, so it is something like this. Let's put the coordinates here. This is z, and this part is 10. So this is z equals x squared plus y squared. Okay, so we want to use this as a rain gauge to measure how much rain falls. Okay, so calibrate this container to measure rainfall. So what does it mean? So suppose there is rain here like this at height h. Okay, so z is equal to h. So what this means, calibrate this, what must h be so that we read 1 centimeter of rain? Okay, so what does it mean, 1 centimeter of rain? Okay, so whichever container you are having, if it is a cylindrical container, we are assuming that rain is falling uniformly. If you have a cylindrical container, if the height is 1 centimeter, you say we had 1 centimeter rainfall today. Okay, here it is not cylindrical. Okay, so if it was cylindrical, if instead of going like this, if it was a cylinder like this, then h equals 1 will give me 1 centimeter rainfall. Okay, so let me explain this. That is, okay, z is equal to 10. So radius is r over square root 10. That is, if we had this, so this part is square root 10 and a cylinder like this, okay, then here 1 centimeter means 1 centimeter of rain. Okay. So we want to find this h, so it will correspond to 1 centimeter of rain. So while at it, we'll find 2 centimeter, 3 centimeter, etc. Okay. So you see this is a volume problem. We know the volume of this. Okay. So suppose here we have k centimeters. So if we have k centimeters here, and assuming that everything is given in centimeters, we know the volume of this. So volume k here is pi r square. R square is 10, so 10 pi times height. Okay, so this is the volume here. Then next we calculate the volume here. Okay, so volume, let's say h, is equal to this integral. Okay, so this integral is, first I integrate with respect to z. So z starts from here, x square plus y square, and it goes up to h. And the projection of this is a circle here. Okay, what's the equation of that circle? Yes? X squared plus y squared is correct, of course, because it's a circle centered here. So what is it equal to if this height is h? H is equal to z. Okay, so the equation of this part is z equals this, so this is h. Okay, so next I describe this. Okay, let's say dx. Dx is from minus square root h minus y square to square root h minus y square. And dy is from minus square root h to plus square root of h. Okay. Yes. Okay. Here I shifted. Okay. So everyone agree with this? Okay. So next we evaluate this, or we can now pass to polar coordinates. Cartesian. Well, this is Cartesian. We'll pass to cylindrical, meaning that we'll express this part in polar. Okay, so that is, we have dz, it goes from r square, okay, x square plus y square is r square, to h. Then I have r dr d theta. I am describing this circle where r is square root of h. So r starts from 0, goes to square root of h, and theta is from 0 to 2 pi. Okay, so you see when I integrate this, evaluate this, I'll get an expression in h. I'll equate this to vk. Okay, so let me see. Well, surprisingly, when you simplify this, this thing becomes pi over 2 h squared. Okay, after all this stuff, when you do this, you get pi over 2 h squared. Okay, so to finish up the problem, VH corresponds to k centimeter of rain, but k centimeter of rain is this thing, 10 pi k. Okay, so here pi over 2 h squared is equal to 10 pi k. Okay, so I want to express h in terms of k. So here h is equal to square root of 20 k. Okay. So now we can calibrate this. Okay, so when h and k, so we can prepare a small table. Or let me do it the other way, because first I want k. When k is 1, h is 4.47. Just to see that things work, 32, 3 equals 7.74. Okay, so once we have this formula, the rest is easy. Okay, so this is a calibration problem. Well, I had a similar real-life problem. An old calculus student phoned me years later that they have a cylindrical water tank. This is real life. Now, cylindrical water tanks do not appear only in calculus books in real life. Okay, they have a cylindrical water tank like this. Okay, so like this. And they pour in water. And of course, if there is a certain height, he can calculate the volume of this. Okay, so the problem was this cylindrical tank was oblique. Okay, so you have this cylindrical tank like this. So it is resting on something like this. Okay. Now here he wants to put calibration to find the volume of the water. Okay. So now you have a similar problem. You have to calculate the volume of this in triple coordinates. Okay, this time it will not be cylindrical because the shadow of this is a rectangle here. Okay, but if it's a rectangle, it's the most convenient for Cartesian integration. Okay, so given height, how much volume does it correspond to? Okay, so this is a real-life problem. Okay, so let me do one more problem. Okay, so maybe I'll pass to spherical coordinates later. So I don't know if I solved this problem. So check your notes. If I solve this, I'll pass to another problem because I have one more problem here. Okay, so this problem, now I forget the number. So whoever is watching, this is problem 81. So you missed all the 80 problems in between. Find the volume of the solid. Okay, so what is a coordinate system? It's an address. Okay, so just like polar coordinates, we prefer to put spherical coordinates and Cartesian coordinates in the same picture. But technically, we have x, y, z here, and again, 3 perpendicular coordinates, spherical coordinates. But just like polar coordinates, we'll draw them here. So if I have a point here, which I call x, y, z, okay, so x, y, z, it means that, okay, so first you go by x some distance, then you go by y some distance, and then you go up to here. by z. That's how you read Cartesian coordinates. Okay, so this is. Now in spherical, we again give three numbers for this. It's a three-dimensional space, so we need three numbers. This is rho, phi, theta. Okay, so when you are using spherical coordinates, you should immediately specify what you are using, because some different notations are used. In our book, throughout, every time we mention spherical coordinates, we use these things. Okay, so here, rho is this one. Rho is the distance from here to here. Okay, so this is rho. So rho is positive or 0. Phi is this angle. So phi tells you how much you are bending away, moving away from the z-axis as an angle. So that means that phi must be between 0 and pi. Okay, because if you move more than pi, then I can also measure it from this side. Then the angle phi will not be unique. We are trying to make these things as unique as possible. And theta is the theta of the polar coordinates. So you drop this here, and then you have the image of this here. This angle is theta. So theta can be anything between 0 and 2 pi. So we write theta between 0 and 2 pi, but generally we don't we don't insist on this much, because we understand what theta is telling us. If you want unique coordinates, then theta must be between 0 and 2 pi. But now that we understand theta tells you how we move around here, so you can have large theta as long as you know what you are doing. Okay, so these are these are the things, the three numbers that will describe us this point. So what are the transition functions, change of coordinate formulas? Okay, so let us call this r, this distance r. Okay, so what is r related to x? X is equal to, of course, first we have x equals r cos theta, y equals r sine theta. Okay. Let us look at this this picture here. Okay, so this is phi, this angle is phi. So what is this angle is perpendicular. Okay, in this triangle, what is r? What is the relation between r and phi? Okay, so what is the relation between r and phi? Sine phi. Sine phi is equal to, well, this is the hypotenuse, right? This is the right angle, so this is r over phi. So r is equal to, this is rho sine phi. Okay, so this part is nice now. Rho sine phi cosine theta. Rho sine phi cosine theta. Okay, what is this thing? This part is z. Okay, so this whole thing is z. And what is the relation between z, phi, and rho? So again, this is the hypotenuse. Z over rho is equal to cosine phi, right? You agree? Okay, he's responsible for this. Okay, then from here we know that in addition to these, therefore z is equal to rho cosine phi. Okay, so as a summary, let me write these again, because this is x is equal to rho sine phi cosine theta, y is equal to rho sine phi, this is sine theta, and z is equal to rho cosine phi. Okay, so these are change of coordinates. And of course, if you take squares of these things, x squared plus y squared plus z squared, you have lots of sines and cosines. As you expect, this becomes rho squared. Okay? So these are the things. Of course, the crucial thing is once you have dx, dy, dz, it must be a correction factor times d rho, d phi, d theta. Okay, so what is this correction factor? So let's do that on Thursday, because I have to draw a picture to convince you. Then I'll explain the algebraic reasoning, and then we'll look at general change of coordinates, which will explain all of the factors we have here without drawing pictures. And don't forget that we have a surprise quiz. Okay, thank you.